Check. 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 Okay, let's go ahead and start. All right, so I closed programming assignment 1. I hope everyone is working on PA2. When is PA2 done? Or due? Wednesday, that's our next, oh no, that's homework, sorry. Does it say February? No. That would be an error if it was. So it's literally 2 days from now, someone said. Okay. Is anybody going to need an extension on that? Okay. I'll go 1 day, and then we'll talk about it again on Wednesday, but not unless you really mean it. Yeah, see, PA2, sorry. Yes, go ahead. PA3 is going to be, I'm going to give you 2 weeks to do that because PA3 is going to be by far, I think, the most difficult assignment. I consider these first 2 where you create this list and exercise it using Lex. These are kind of like warm-ups. I consider them to be something that you could have been given in 12B. Go ahead. I said, yeah, the hardest of the course, yeah. It's actually harder, I think, than PA 4 and 5. Even though 4 and 5 are in C and 3 is in Java, it's harder because 4 and 5 are just, in a way, a matter of translating algorithms that are in the textbook. But I'm not giving you any algorithms, and some of the things you have to do in PA3 are, difficult, and you have to figure out how to do certain things. No? Go ahead. No? Okay. Are there any questions on PA2? Maybe I should go that route. I guess we've been answering questions. All right. So where did we leave off last time? We left off, we're in the middle of the handout on asymptotic growth rates. So let's pick up, the last thing I did, I think, was I gave you an exercise. So let's begin at the next definition. So here's another set of functions. Little o of f of n is the set of functions f of n such that for all positive c, there exists positive n naught, such that for all n greater than or equal to n naught, the inequality 0 less than or equal to f of n strictly less than c times g of n holds. It's a new set of functions. A new quantified sentence, a very similar inequality, but the quantifiers are different. This is little o. I think it's very helpful to hold this up next to the definition of big O. Recall, big O of f of n is also a set of functions such that there exists a positive c, there exists n naught, positive, such that for all n greater than or equal to n naught, 0 less than or equal to f of n less than or equal to c times g of n. Now if you look carefully, you'll see there are two differences. One of them is a very minor difference. The other is an absolutely major difference, a huge, gigantic difference. What are the two differences, and which is the small one and which is the big one? Strict versus weak inequality, universal versus existential quantifier. Thank you. Of those two, which is bigger? The quantifier? The quantifier is much bigger. The quantifier says much more. Here we're insisting that something be true. This is a minor difference, and we could have replaced this by strict. We wouldn't get a different set of functions. We could replace this by weak. We wouldn't get a different set of functions. So it wouldn't really have any effect. It's for convenience that we put strict there. But this makes this sentence much stronger. It's a much more restrictive sentence. It's much harder for something to be true for all positive numbers than for some positive number, c. All right, so when we hold these two sets next to each other like that, it's obvious that one is a subset of the other. You think little o is a subset of big O, or big O is a subset of little o? How many people think big O is a subset of little o? Raise your hand. How many people think little o is a subset of big O? Huh? It's not a trick question. Okay, so, and how many people are afraid to raise your hands? How many people are afraid to admit that you're afraid to raise your hand? Okay. All right, most people didn't respond to that poll. Maybe this is one reason why I should have clickers, right? Would you like it if I had clickers? Nobody likes clickers, okay. Well, anyway. Obviously, little o of g of oops, first of all, there's another problem. This should have been g of n. Right, what goes inside the notation is some fixed function. And it defines an entire set of functions. And this set of the general function is not the same as what's in parentheses. I apologize for that. I don't know where that came from. It was just... So little o of g of n is a subset of big O of g of n. Why? This is like a club that's harder to get into. Let's put it this way. The rest of the sentence is essentially the same from the existential, there exists n greater than 0 onward. The rest of that sentence is essentially the same. If something, namely this, is true for all c, then it is certainly true for some c. So therefore, any function belonging to this set must belong to this set. The converse is false, however. It's possible for this sentence to be true for some c. We've already seen that if it's true for one c, it's true for infinitely many, but that's still a long way from all positive numbers. So this can be true without the for all being true. So this is, in fact, a strict subset. Go ahead. Cannot hear you. Louder.
What is the difference between infinitely many and all?
Okay. Now think of what that inequality c greater than 0 is talking about. It's talking about the right half of the number line, the real number line. You have a picture of that in your mind from your calculus class, right? Everything but 0, everything to the right of 0. Okay, there are infinitely many points on that number line, right? Okay, but lots of subsets. If I pick 1 and say everything bigger than 1, that's also infinitely many, right? But it's not all, right? So, so I don't want to include this in the notes, but note that here's 0. All says all. Here's 0. Say 1 is the smallest C that'll work. This is sum. They're both infinite. Neither one is bounded above. No. I mean, some infinities are bigger than others, but this has nothing to do with it. These are both infinite sets. This is all positive real numbers. This is some positive real numbers. Okay? Right? There's a bunch of positive real numbers that aren't in this set. And that is possible. Okay. Going on. What do we say if f of n is in little o of g of n? We say, and we use the same, we write the same thing, right? Instead of f of n, an element of little o. And we say g of n is a strict asymptotic upper bound. For f of n, or that f of n is strictly bounded above by g of n, asymptotically. All right, so we need some examples, and I'll give you some examples. Before we do that, let us look at another way of saying the same thing. F of n is little o of g of n if and only if the limit as n goes to infinity of f of n over g of n equals 0. Let's just look at what that limit statement says for a second. Even though f of n and g of n might be going to infinity, the top, rather the bottom, is going to infinity so much faster than the bottom. I'm sorry, the bottom is going to infinity so much faster than the top that the quotient itself goes to 0. That's what is supposed to be embodied in this statement. G of n is a strictly faster asymptotic growth rate than f of n. Okay, let's prove this. Notice it's an if and only if. Well, observe f of n is in the class little o of g of n, if and only if, what was the definition? We just looked at the definition. That sentence is true, so let's repeat that. Sorry. If and only if, for all positive c, there exists n naught, positive, such that for all n greater than or equal to n naught. Well, let's take this inequality and do one thing to it. Divide all terms by g of n. Now that's possible only because we decided to put strict inequality here. Right, because c is positive if this is strict inequality, then g of n must itself be positive, because if g of n were ever 0, this quantity would be 0, but that's forbidden by that inequality. So since g of n is not 0 for n greater than or equal to n naught, I can divide by it. So we get this inequality, 0 less than or equal to f of n divided by g of n strictly less than c. All I did was take the inequality from the definition and divide through by g of n. Now let's just stare at that for a second and notice that it is the very definition of this limit statement. This is not a deep theorem. Okay? What is the tell me, do they ever give you the definition of this limit statement in calculus classes anymore? Okay, did they ever give you the epsilon delta definition of limits? Okay, so this is slightly different because it's not a point you're approaching, it's infinity, but it's the equivalent to the epsilon delta definition. The way they say it in words is this: the quantity in parentheses can be made arbitrarily close to 0 by taking n sufficiently large. But that's exactly what this quantified sentence says. The word arbitrary is encoded in this universal quantifier. For any positive c, for any closeness to 0, c is a measure of how close you are to 0. For any closeness to 0 you want, there exists a sufficiently large n naught such that if you're past that, you're that close to 0. That's exactly what this limit statement says. All right. End of proof. Now, so therefore I could have taken this as the definition, and in fact many textbooks do take this as the definition of f of n little o of g of n. Of course, those people would have had to have rewritten it this way in order to see that little o is a subset of big O. All right. All right, so some examples. Functions that are strictly slower growing than other functions. Example. Natural log of n is little o of n. Now, why? Well, according to the lemma, what we need to do is take the limit of natural log n over n. That's what the lemma says. And this limit will be 0 if and only if that statement is true. Okay? Now, look at the top. Natural log n. As n goes to infinity, that blows up. It goes to infinity. Look at the bottom. N. As n goes to infinity, n goes to infinity. Okay? The top goes to infinity. The bottom goes to infinity. There was a name for that in your calculus class. It was called a indeterminate form. Whose rule do you use when you see an indeterminate form? L'Hopital's rule. Okay, so what did L'Hopital's rule say? It said that this limit can be replaced by what? Take the derivative of the top, not the quotient rule, guys. Just differentiate the top, differentiate the bottom. What's the derivative of the top with respect to n? 1 over n. What's the derivative of the bottom? 1. So this is the limit of 1 over n, simplifying. N goes to infinity. And what do you get? You get 0. So that proves this. Now, last we proved something, and it was an easy proof. So these limit theorems I'm going to give you are very useful because they allow you to prove that one thing is little o or big O of another without having to go to the definition by taking limits. They're sometimes not valid, and we'll talk about that. Quick question. I don't remember that. I just remember that it wasn't 400 pages when I saw it in calculus. Go ahead. It shouldn't have been. The calculus book was 400 pages, but L'Hopital's rule had a shorter proof than that. Go ahead. Possibly. Yeah, I mean, look, you don't need to prove L'Hopital's rule. You don't need to reinvent that wheel. But when you're, what is a proof? A proof is a sequence of sentences, right? And it starts with a hypothesis, ends with the conclusion. Each step has to either follow, using some inference rule from previous sentences, or some previously proved fact. I consider L'Hopital's rule to be a previously proved theorem that you are free to use anytime you want. So just say, at the appropriate moment, by L'Hopital's rule. Okay? So that's really what I should be writing here, but I'm not going to bother. Okay. Are you going to lose a point? I doubt it. Let's hold the questions, please. I've got to move along today. Okay. Here's an exercise. Show that natural log of n to the power p is little o of n to the k for any p greater than 0, k greater than 0. They don't even have to be integers, actually. All right, it's also L'Hopital's rule. It's just the number of applications of L'Hopital's rule is going to depend on p and k. What this basically says is that every polynomial defeats every log function. Here's another exercise that is practically the same thing. The only difference is the differentiation becomes a little harder, right? Why did I choose natural log? Because that's the easiest log to differentiate. Show any log base b of n to the power p equals little o n to the k for any p greater than 0, k greater than 0, and any base, let's say, greater than 1. I'm not really interested in bases between 0 and 1. So what this says is that any polynomial, no matter how small the degree, defeats any log function of any base, and no matter how high the degree. This is all polynomials defeat all logs. They're faster growing functions. So in the hierarchy of growth rates, the log functions are down here, the polynomial functions are up here. That's what this says. That's a basic fact that you need to be aware of. Here's another example. N to the k equals little o, is in the class little o of e to the n for any k greater than 0. Okay, proof. Well, as before, we need to show that the limit n goes to infinity of n to the k over e to the n equals 0. And again, the top is going to infinity. It's a polynomial of degree k. The bottom is going to infinity. It's an exponential function in n. Okay, but the question is, who's going to infinity faster and who's going to infinity slower? Well, it's an indeterminate form. Let's apply L'Hopital's rule. So differentiate the top. I get k n to the k minus 1 over, how do you differentiate e to the n? E to the n, that's why I have it here, because it's my favorite function of all time. It's its own derivative, should be your favorite function, is a distinguished function for that reason. Okay, so we can pull the k out. Is it still an indeterminate form? Is the top going to infinity or not? Well, that depends entirely on what k is. If k was 1, then this is n to the 0. It's a constant on top. The bottom still goes to infinity, and it's not an indeterminate form. It goes to 0. But if k is bigger than 1, I have to differentiate again. And I would get k times k minus 1 times n to the k minus 2. And then I'd ask, what's the actual value of k? But after you've applied L'Hopital's rule enough times, you eventually get to 0. So I'll leave that as an exercise to fill in the dots and get 0, which proves this. By the way, how many applications of L'Hopital's rule? How many? K? You'd be right if k were an integer, but I never said k was an integer. So answer, it's ceiling k. Ceiling k. So if k were 1/2, for instance, I'd have to do L'Hopital's rule 1 time. Or if k were 3/2, I'd have to do it 2 times. Check that. Okay, that's, check. Okay. So L'Hopital's rule wasn't shown to you for nothing. It's a very useful fact. So now okay, here's another exercise. E to the n, suppose I change the base, show that limit, or rather n to the k equals little o of b to the n for any k greater than 0, b greater than 1. It's the same thing, except the differentiation is a little more complicated. The differentiation, has a constant in it that gets that piles up out in front in the denominator and can be pulled out of the limit. It's either log of b or 1 over log b, I forget what. Okay, so what this says is that every polynomial is defeated by every exponential, no matter what the base. So, in this hierarchy, at the bottom are the log functions, in the middle are the polynomial growth rates, and the really fast-growing functions are the exponential functions. They defeat and are faster than all the polynomials. So those are the really bad algorithms, right? Those are the algorithms with the high growth rates. In other words, you have to do a lot of work. The amount of work you do scales up really fast with the input size, and they become totally impractical for even moderately sized input sizes. That's a feature of exponential growth rates. You don't like algorithms here. You love algorithms that run in log time. Can you think of an algorithm that runs in log time? No, merge sort ran in n log n. Binary search. Binary search is the classic example. Okay, so here's another exercise. Show that little o of g of n intersect big omega g of n is empty. So there are no functions that are bounded above strictly by g of n, and also bounded below weakly by g of n. Kind of makes sense when you put it in words, right? These are the functions that grow no slower than g of n. These are the functions that grow strictly slower than g of n. So there's nothing in between. There's nothing that does both of those things. It's not enough to just say it that way. You need to actually put this definition down, write this definition down, assume you have a function that satisfies both definitions, derive a contradiction. I believe this is going to be a homework problem, if not in PA2, or rather homework 2, maybe homework 3. Okay, so here is another definition. Oh, by the way, every time that we show that one function is little o of another, we've also showed that it's big O, right? Because little o is a subset of big O. So n to the k is big O of e to the n. And also, natural log is big O of n, because little o is a subset of big O. If it's true, it's not always true. Yeah, I mean, I hesitate to answer these questions that have the word always in them. Okay? Prove what you're supposed to prove, nothing more. Okay, definition. 5. Okay, little omega g of n is set of functions f of n satisfying for all c greater than 0, there exists n naught greater than 0 such that for all n greater than or equal to n naught, 0 less than or equal to c times g of n strictly less than f of n. Okay? Here we would say that, I wrote it correctly this time, I'm supposed to have a g of n here. Here we would say that g of n is a strict asymptotic lower bound to f of n. And here are some exercises. Oh, maybe I should do what I did last time and put this side by side with the definition of big omega. Big omega g of n is functions f of n satisfying there exists positive c, there exists n naught, such that for all n greater than or equal to n naught, 0 less than or equal to c times g of n less than or equal to f of n. As before, two differences, a minor difference, strict versus weak, a major difference, universal versus existential quantifier. But this allows us to see directly that little omega has to be a subset of big omega. Obviously, little omega g of n is a subset of big omega g of n. Now I'd like you to prove the analogs of what I just proved for little o for little omega. There's a characterization as a limit. And also, little omega does not touch big O. Little o does not touch big omega. Little omega does not touch big O. So there's a duality between omega and O, if you think about it. So exercises. First, I'll call it A. Show the limit f of n is little omega, g of n if and only if limit n goes to infinity of f of n over g of n equals infinity. If you think about what that says, the top grows so much faster than the bottom that the quotient goes to infinity. Even though the denominator might be exploding, the numerator is exploding faster. So this says that f of n is a faster growth rate than the bottom. F of n is strictly bounded below by g of n. That's exercise A. exercise B. Little omega g of n intersect big O of g of n is empty. Again, assume you have a function that satisfies both definitions, derive a contradiction. Therefore, no such function exists. So therefore, this intersection is empty. Okay. Now, these two limit theorems each are of the form if and only if. It's really just a matter of showing that this is equivalent to this, the definition of this limit. Here's another theorem. Isn't there some way to characterize big O and big omega using limits? There is, but the converse is not going to be true in those cases. So here's a theorem. If limit f of n over g of n is L, where L is in the range 0 to infinity, but not including infinity, then f of n is big O of g of n. So if this limit exists, and this limit is either 0 or a positive real number, not infinity, then f of n grows no faster than g of n. Note or remark, the converse is false. Just because f of n is big O of g of n does not imply that this limit statement is true. In fact, this limit might not exist, even though f of n is big O of g of n. I'll show you that in an example. I'll show you specific functions f and g for which this is obviously true, but this limit doesn't exist, even in the sense of being infinite. All right, but first let's prove this. These limit theorems seem a little technical at first, but they're a boon. They're a wonderful thing because they make, these limit theorems are what's going to make everything you want to prove almost a triviality. It really boils down to your skill in taking limits and computing limits when you want to compare two functions. Okay, here's the proof. The limit statement says what? What does the limit statement say? It says, for all c greater than 0, actually they don't use c in calculus textbooks, for all epsilon greater than 0, there exists n naught greater than 0, such that for all n greater than or equal to n naught, the quotient can be made close to L. How close? Epsilon close. Absolute value of f of n minus over g of n minus L. So that's the distance between this quotient and the thing that it's supposedly getting close to. That difference can be made arbitrarily small. Again, the word arbitrary is encoded in the universal quantifier. You tell me how close you want this quotient to be to the number L. There exists a point far enough to the right on the n-axis such that from that point further to the right, it will be that close. That's what this asserts. And that's exactly what we mean by this limit. Okay. So notice this holds for all epsilon, which means any particular epsilon you care to pick, as long as it's a positive number, you just pick it out of the hat, just at random. There exists an n naught, making the rest of it true for that epsilon. All right, so let's pick a particular epsilon. Pick epsilon equal 1. Then, what? The definition above says, for this epsilon, 1, there exists n naught greater than 0, such that for all n greater than or equal to n naught, absolute f of n over g of n minus L is less than 1. Just replacing epsilon by 1. Why 1? It's true for all. And you might say, where'd you get the 1? Okay, but you know now not to ask that question, right? See if the 1 is okay. That's what you're trying to do. Check that the 1 works and gives me what I want. What I want is all the constants that go into this definition. That's what I'm trying to reach. Okay. So that repeats. Let's just rewrite that. It says if the absolute value of a number is less than 1, it means that the number of itself is between -1 and +1. Right? If absolute value of a number is less than 1, then that number has to be in the range -1 to +1. Now, we don't care about the left-hand side. So this implies, therefore, there exists an n naught such that for all n greater than or equal to n naught, the inequality. So let's forget about the left-hand side, pull the L over to the right. F of n over g of n is less than 1 plus L. So therefore, there exists n naught greater than 0 such that for all n greater than or equal to n naught, let's multiply both sides by g of n. F of n is less than, and if it's strictly less than, it's less than or equal to. Right? This implies this. The number 1 plus L times g of n. And now, remember, all functions under discussion are asymptotically non-negative. So therefore, by our blanket assumption, there exists n naught greater than 0 for all n greater than or equal to n naught. 0 less than or equal to f of n less than or equal to 1 plus L times g of n. Now, is this getting to look a little bit closer to the definition of f of n being big O of g of n? What is this C? 1 plus L. And is 1 plus L a positive number? Yes. Why is it a positive number? Because L is non-negative. So 1 plus L is certainly strictly positive. So let C equal 1 plus L in the definition of big O of g of n. Then C is positive since L is greater than or equal to 0. And we have that f of n is big O of g of n. And that was what we wanted, end of proof. Might have seemed long, but it was really nothing but exercise in unwinding a definition of a limit, picking a specific epsilon and packing it back together into the definition of big O. By now you are hopefully aware that every time I have a theorem that involves big O, there's sort of a dual theorem involving big omega. Let us state it. If limit as n goes to infinity of f of n over g of n equals L, where this time L cannot be 0, but it can be infinity, then f of n is big omega g of n. And same remark, the converse is false, and I'll show you that. Actually, I think I might give you that as an exercise. Now, I could leave this as an exercise. I could prove it, kind of like we just proved the last one. But interestingly, it follows from the last theorem and a well-known fact about limits, namely, the limit of a quotient is the quotient of the limits. Or let's put it this way. The reciprocal of a limit is the limit of the reciprocals. Do you remember that? So if you know limit of f of x, then limit of 1 over f of x is 1 over limit of f of x, right? This reciprocation operation goes through the limit. So let's prove it using that fact. The limit statement says that limit of g of n over f of n, the reciprocal, is equal to L prime, where L prime is the reciprocal of L. And hence, since L is in the range 0 to infinity, not including 0, L prime is in the range possibly 0, not infinite. Now let's just, in order to understand this, you have to think of the reciprocal of 0 as being infinity and the reciprocal of infinity as being 0. Well, that's true in the sense of limits. So that's okay. So by the last theorem, then we have g of n, the top, is big omega of the bottom. I'm sorry, big O of the bottom. I said omega, I meant big O. But didn't we also prove, one of our first theorems was that this is true if and only if f of n is big omega of g of n by a previous theorem. F of n is big omega of g of n. And that's what we set out to prove. End of proof. Okay, so let me try to draw a picture now. We have these limit theorems. And let's start to get a Venn diagram of these sets of functions. here's big O, G of n. Here's big omega, G of n. And their intersection is theta, G of n. And let's consider the set of functions where the limit L exists. D, N, E. That's what they write in your calculus classes for. It does not exist. So let L equals the limit of the same quotient, f of n over g of n, if it exists. That's what L stands for. Okay? So we have a name for this area of of big O. That was called little o. Little o of g of n. So that is this part only, because little o does not touch big omega. This is where L equals 0. It stops here. Make sure we see that. And this is little omega, g of n. This is where L equals infinity. And it stops here. By the exercise, little omega does not touch big O. So this area right in here, this is where L is strictly between 0 and infinity. Didn't make it big enough. I always try to make it big enough and it doesn't work. If we had any sense, we'd call this little theta. But nobody calls it little theta. So if you start calling it little theta, everybody else will be confused. Don't do that. Right? The bigs are on top and the littles are on the bottom. We should call that little. So the littles are where the limit exists. So notice this L between 0 and infinity, that's actually part of theta. So we have an additional theorem that says if limit f of n over g of n equals L, where L is between 0 and infinity, a positive real number, in other words, then f of n is theta of g of n. Now, this actually follows directly from the previous two theorems, doesn't it? Because from that inequality, we get f of n is omega. From that inequality, we get f of n is big O. So therefore it's in the intersection, so therefore it's in theta. Right? It's the intersection of the two intervals. Note, the intersection of the interval 0 to infinity, not including infinity, intersect not including 0, including infinity, is the interval from 0 to infinity. That's the way you should see this. If L is in here, we're in big O. If L is in here, we're in big omega. If it's in both, we're in both. So this interval corresponds to theta. So this gives us a nice picture. If you just memorize this picture, you have all the limit theorems and the relationships between big O, big omega, and theta, and little o and little omega, all contained in this picture. The only thing about this picture that we haven't established is this space up here, and this space right here. A lot of people, a lot of students are tempted, because they want to simplify, right? They're tempted to believe that these spaces are empty. There's not really anything there. The limits always exist. Unfortunately, that's not true. So I'm going to show you there really is something here. I'm going to call this example A. This example A shows that our first limit theorem, the one giving us big O, has its converse is false, right? It's possible to have a function in big O of g of n and yet the limit not exist. So let me call this example A. Let g of n equal n, and f of n, here's a weird function, 1 plus sine of n times n. Straight away you think, well, that's not the kind of function that's going to come up often in algorithm analysis, and it doesn't. So we don't need to worry about this too much, but I just want to show you that this space exists. Can't logically infer that the limit, that just because f of n is big O of g of n, the limit exists. Okay, so let's try to figure out everything by graphing these two functions. Here's the n-axis. Here is 2 times g of n. That's the line 2n, right? I know, it doesn't look like the slope is 2. Pretend the slope is 2. Then let's graph that function. How in the world are we going to graph that? It's easy. Sine, you know, oscillates up and down between +1 and -1. Add 1, the thing in parentheses, oscillates up and down between +2 and 0. +2, 0, +2, 0, and it's sort of, its average is 1. If you multiply that by n, the result oscillates up and down between n at the top and 0 at the bottom. So these two lines are its envelope. Notice this function is asymptotically non-negative, but not asymptotically positive. It's 0 infinitely often. Okay, so observe, obviously f of n is big O of g of n. Why? Because there's a constant I can multiply g of n by such that f of n is always below it. In fact, I can take n naught to be anything I want. This is always for all n, not just all n greater than or equal to some particular positive n naught. But also notice f of n is not big omega g of n. Does everybody see that? For that to be true, I would have to be able to multiply g of n by a positive number that would put the graph below all the troughs. Right, think of that 2 as being a little volume control. Replace that by c. As it gets bigger, you're turning up the volume. As it gets smaller, you're turning down the volume. But as long as the slope is positive, you'll never be below any of the troughs, much less, infinitely many of them, all of them past some point. So f of n cannot be omega g of n. No c will work. You can't multiply any c times g of n to get it below f of n forever. But, so f of n is definitely in this region over here. It's not in big omega, so it's somewhere over here. But the limit doesn't exist. Why does the limit not exist? But let's just look at f of n divided by g of n. If I take this function and divide by n, the n's cancel, and I get 1 plus sine n. And the limit does not exist, even in the sense of being infinite. It just goes up and down forever. It doesn't approach any number, even infinity. So the limit doesn't exist. That's why I chose sine here. All right, so this really is a function in this space here, and it shows that it's not empty, and it shows that the converse of that first theorem is false. It's possible for f of n to be in big O of g of n, and yet the limit of f of n over g of n does not exist. All right. There's also an example B. So I'm going to ask you to read that. It's in the handout. See example B in the handout. And here's an exercise. Find example C, i.e. f of n, specific functions f of n, g of n, such that f of n is big omega g of n, but the limit as n goes to infinity of f of n over g of n does not exist. So example C is going to be out here. So I just gave you example A. You read example B. You invent example C. Now, I promised you that once we got through these limit theorems, and we have, that we'd go back to this example where we said n plus a to the b is theta n to the b for any a, b real numbers, and b had to be greater than 0. I gave it as an exercise last time for you to do that and do it directly from the definition. How many people did that? I see one person raising their hand. Okay. Is it because, how many people, I don't care if you succeeded, how many people tried to do it? A few. Okay, that's like maybe 3 people. That disappoints me. You should try to do it. You're not going to be able to absorb these definitions until you try to apply them. Okay, but now that we've done all these limit theorems, this becomes a triviality. Proof. What do? Take the limit. Look, even though the converses of these limit theorems don't hold, if you can compute a limit, you can prove something. That much does hold. Limit as n goes to infinity of n plus a to the power b over n to the b. Well, that should be something that you can compute, and you should have learned how to compute such a thing in your calculus class. First of all, that's limit of n plus a over n all to the b. And the Beef power function is continuous, which means I can take the limit inside the function. In fact, that's the definition of continuity. Again, I consider these previously proved facts, anything you learned in your calculus class. So this is equal to limit as n goes to infinity, all to the power b of n plus a over n. But if I simplify that, I get 1 plus a over n. What's that limit? That's 1, right? Because as n goes to infinity, this goes to 0. And notice it doesn't matter what a is, positive or negative. This term goes to 0. So what's in parentheses is 1. So this is equal to 1 to the b, which is 1. Now, why does that end it for us? Because of this theorem, right? The limit is between 0 and infinity, this theorem right here. If the limit exists and it's a positive real number, not infinity, not 0, then f of n is theta g of n. So since 0 less than 1 less than infinity, n plus a to the b is theta n to the b. Now, there are a bunch of exercises at the end of this handout. Some of those exercises are homework problems due this Wednesday. I'll go over some of the exercises here and possibly some of the homework problems, just because I don't consider myself quite done with the handout until I've done some of the exercises. But there's one homework problem that I haven't covered it at all. And that is problem 7. Now I could, and I'm considering taking it off. You want me to take it off, or do you want to just read the next handout, read Stirling's formula and apply it? Take it off. You're talking about taking this off, right? Okay. That's hilarious. No, that's bad. Okay. No, don't go there. All right, so I'm going to move problem 7, over to homework 8. You don't have to do it. If you already did it, save it and turn it in. What did I say, homework 8? Homework 3. Got my digits mixed up. All right, I will see you on Wednesday. Homework due on Wednesday. 6 problems, not 7, and I'll change that. Go ahead. By the way, anybody who's still trying to get into this class and was on the wait list, you should be talking to me this week, because this is the last week to add. Friday's the last day to add. Take care.